section 6.5. So if you remember a lot of chapter 5 and chapter 6, we have all the different square root functions, cube root functions. We've talked about how we can write them in different formats, so we'll review that a little bit. But 6.5 is that little section that usually happens for each of our chapters where we actually get to look at the graphs and see what the graphs of our different functions look like. So that's what we're going to do today. Obviously, the graphing part is pretty easy when you have a graphing tool, but then we want to look at also the domain and range. So that'll be a good review of what is the domain and range and how do we find that on our graph. So we'll start with number 1 here. And actually, I'm going to start with the even easier format of this. So Connor, or if you're watching on YouTube, if you want to kind of split your window and you can graph and Desmos at the same time, I'm completely fine with that. Or if you have it on a different device next to you, that works too. So actually, I'm going to start off with the really kind of the basic function, which is y equals the square root of x. Okay, so you can see when we graph y equals the square root of x, we kind of get this interesting graph going on, right? It starts at 0, and over the positive values, it's true, but you can see we don't have any values in any of the other quadrants. It's only in our first quadrant here that we have any values for this function. So let's think about, why does this graph the way that it does? Well, it's because we have a square root function, right? We can't have a negative value in here unless we want to start graphing on the imaginary plane, which I don't think any of us want to do. So we're just going to be happy that we get to stay with our real numbers. And we know that for example, if I try to put in -1, square root of -1 is actually I, our imaginary number. Square root of -2, can't do it. The calculator is just going to tell you undefined. So we know we cannot ever have an x value that is negative. So that makes sense why we don't have any part of our graph that's graphed to the left-hand side, right? The other thing that we notice is that all of our y values are also positive. So that also makes sense because there's no way that our square root function can ever become negative, because in order to do that, we would have to somehow have a negative inside the function, and that's just not going to work out. So when we see this graph, at first you're kind of like, huh? But then if you kind of break down, what am I graphing? I'm graphing the square root of x. And the square root of x should always have to be positive, and the square root of x should always have to be positive. So we end up with this graph. And then obviously you can copy this and, or graph it on your paper. Now, when it comes to the domain and range, just a reminder, because it's been since before Christmas that we talked about domain and range. The domain refers to your x values. Your domain is your x values, right? And so for this particular function, we would say that our domain is x has to be greater than or equal to 0. We can do a square root of 0, so that's an okay value. But x has to be greater than or equal to 0. And then our range, is our y values, right? And that's also the case for y. All of our y values for our range, y, have to also be greater than or equal to 0. So that's what we're going to do. We're going to talk about the domain and range. We just have a couple of them to do and check out if it's graphing as expected. So close that. Okay. So then if I go back to my notes, I think the original one was okay. Yeah. So what happens? Yeah, thanks. My computer's beeping at me. If I put negative. So this is as we would expect the negative. We have the negative square root of x, and the negative sign is outside of my square root. So it's making whatever the square root is negative. So that's flipping the graph across the x-axis, right? And then just to prove a point, if we try to put in, oh, it will kind of work in there because it's just taking the negative x value. But, oh, if I try to put in like -2, it's undefined. That's what I was trying to do. All right, so we are trying to graph negative square root of x, and it's actually -3 square root of x. So if I just put up my original y equals, I'll just do negative root of x. So again, we're kind of talking a little bit about transformations, and these transformations happen across the board. So if you make a function negative, like we went from positive square root of x to negative square root of x, it's flipping it about the x-axis, right? So just to kind of compare the two, the purple function is the one that we're actually looking at. This is the black function shows y equals negative square root of x. So we've flipped the square root of x over, and then we've multiplied by 3. So when you multiply by 3, everything's just going to increase, or in this case, decrease faster because you have a multiple of 3 for every x value. So then what would we say that the domain and range for our purple curve is? So I would say that the domain is, I'm trying to write it here. Let me pull it over here. Okay, so the domain, again, is our x values here. So our domain is x is greater than or equal to 0. Because again, 0 is one of those values, right? But whatever x we use has to be greater than or equal to 0. Our range is our y values. And our range this time is going to be that y is actually less than or equal to 0. And that is because of our negative sign. So the negative sign affects the range. The multiplying by 3 actually does not affect the range. It's just kind of keep it in the same spot. Exciting stuff, right? All right, so let's go back to our notes here. So that's the first one, square root function. You may at some point be asked, like on a test, not from me, but I'm just saying, like on an ACT, SAT, pre-calculus kind of thing, you might be asked to identify what a square root function is. And square root functions are pretty easy to find because they have, you can't have negative x values. So that should kind of be your tip off that it's some kind of a square root function. If you see kind of that, half the graph chopped off. Okay, so let's talk about number 2 here before I pop it into Desmos and we see what it looks like. We have y equals -1/2 cube root of x. So if you remember back, and I think I even have my notes on here. Yes. If you remember back to here, okay, 6(1), we talked about, this is actually a cube root function here, the cube root of b. Another way we could write this is b to the 1/3 power. So depending on what calculator you use, you might have to put a cube root or a fourth root function in as, to the 1/3 or 1/4 or 1/nth power to be able to put it in. Desmos and TI calculators both have the functionality to put in different roots, but if you're ever like just with a scientific calculator, they might not have that functionality. So don't forget that we have this relationship where we have the cube root is equal to 1/3 for the exponent. Yeah, so I just wanted to point that out. All right, so now let's go into Desmos. And we are going to just graph, let's just start with the cube root function first, okay? So if I want to graph it in Desmos, I can't actually, well, I could, but that would not be correct. I don't just use the square root function. I actually need to go under my functions, And I think it's miscellaneous, yeah. And then underneath there, you see this nth root function. So that's what we want to use, nth root. And then you have the opportunity to put in there 3. And then this is x. See, this one looks a little bit different, right, than our square root function. I just want to point out, if I also would graph y equals x to the 1/3 power, that you're going to get an identical graph. So these mean the same thing. We said that algebraically, but I think sometimes visually it helps to see. So if they're exactly over top of each other. All right, so what's happening with our cube root function? So the cube root actually can have some negative x values. And why is that? We got to think about that a little bit. Why can a cube root have negative x values and a square root cannot? Seems like it's more complicated, so it should have more restrictions, right? So if you think about what a cube root means, that means that you're multiplying 3 times, right? So when you multiply, let me see if I... All right, so if I have, for example, let me take a step back. If I take the cube root of -8, for example, right? I am saying what multiplied by what multiplied what? What multiplied 3 times gives me -8. And I know that -2 times -2 times -2 give me -8. So even here on my graph at x equals -8, you can see that there's a value y equals -2. And that's because a long time ago when we learned about multiplying and dividing negative numbers, remember, if you have an even number of terms that you're multiplying or dividing, then you end up positive. And if you have an odd number, you can end up negative. So that has to do with the fact that you're multiplying an odd number of times, why you can take the cube root of a negative number, but you can't take the square root of a negative number. Okay, so then when it comes to my graph, okay, the domain, remember, domain is my x's. The domain goes out to positive and negative. So we would say that this is all real numbers, right? And what about my range? My range is my y's, right? And this way. So that also is all real numbers, not hashtag numbers, all real numbers. And this is a little bit, I think it's easier to see the domain. You can see it going on forever and ever. But if I actually go back to my graph that I can scroll a little bit on, I mean, if I zoom way out, you can see that eventually the range is growing much more slowly than my domain. But you'll see eventually you will be able to reach any number. There's no bound to that. You're just going to have to go to a really big X to get your Y really big. Okay, so that is y equals the cube root of x. And the problem was what happens if we make it negative? Okay, so if we make it negative, it makes kind of a pretty color pattern, right? Can do some Desmos art. Again, the negative is just flipping it over the x-axis. And then the original problem also had it halved. So then it's making it grow, it's multiplying by half. So it's growing or decreasing half as quickly. So you can kind of see how that is. Now the blue function, right? The purple one is the one we just did. The blue function will have the same domain and range. So the domain of the blue function is going to be all real numbers, all real x's, right? And the range is also all real numbers. This is not on your paper, but I think it's worthwhile doing. What if we just graphed all of the, I think it's a good little exercise. It'll take a minute. What if we graphed all of the roots from like 2? So we start 2, 3, 4, 5, 6. Yeah, let's do that. Oh, that's fun to see, right? So if I turn on only the even roots, so the square root of 2, square root of 4, and square root of 6, they're all like in the purpley green category. There we go. We'll change that one to black. There we go. So you can see that all of the functions, they operate a little bit differently, right? And how fast they're rising and trailing off. But they are all only valid when x is positive. And that has to, again, to do with the fact that you're multiplying an even number of times to get the value inside. So you can't have an odd number or a negative number. And then if we turn those off and we put on our odd functions, you can see that these have a similar shape, just slightly different. And these are going to be true for all values of x and y. The domain is going to be all values of x and y. Okay. And this is just a good old combine a bunch of things together. This is probably before we go graph it, and I can't even guarantee that I'm going to get this exactly right, but let's think about what we think is going to happen. And my brain is a little bit rusty too. So you're going to have to bear with me as I graph this. So I'm going to open this in Paint. Okay, so we have -2 times the cube root of x plus 5 and plus 5 on the outside, right? So let's kind of, before we just throw it in Desmos, let's kind of stretch our brains a little and see if we can remember what each of these things do. So we talked about this first, this negative, right? What's the negative, the -2, but really it's the negative going to do? The negative is going to flip my whole graph on the x-axis, right? So if it's a cube root function and it usually looks like this, it's going to look like this now. Very high-tech drawing, okay? It's going to look like that now. And that's because of my negative sign. I know that's true, right? Out here, I have we'll deal with the inside last. Out here, I have a +5. Okay, so the +5 is happening outside of my function. My x is all in here. The +5 is kind of at the end, right? So what does that do to my graph? Does that shift my graph on the x or the y-axis? Do you remember, Connor? Y. I agree with you, right? It's going to shift it up on the y-axis because it's just like you're adding 5 to the whole value. So this is going to shift up 5 on the y-axis. Okay. And then we have our last guy in here on the inside of the function, on the inside of our cube function. What I'm talking about here is you have x plus 5 if I pull that out. So we have this +5, and this is happening inside the function. So when it's inside the function, that means that it shifts, and by process of elimination, it shifts the x-axis, right? And remember, this is the weird one where when you add 5, when you add inside the function, it actually is going to shift it to the left. And when you subtract, it's going to shift it to the right. So I'm going to say we're going to shift left 5. Shift left 5. So let's see if we're right. Because again, I am rusty, so. Also a good thing to know how your graphs shift. Okay, -2. So yes, flipped it over, right? Oh, it made it a little fatter because we're multiplying everything. Then when we add in the plus 5, oops, 5. Okay, let's just zoom out a minute. Okay, so it did shift my graph to the left 5, right? And then when we add our plus 5 on the end, it shifted my graph up 5. So my new kind of origin point is here at -5, 5 versus down here at, if I graph my original function, well, we'll just do the negative. There we go. So that's, excuse me, that's the original function. This is the new function. It's gotten shifted and it got fatter, right? And we know what in the function did that, what each number in the function represents in terms of doing that. So that's pretty much it. That's what I wanted to cover today is graphing. On Monday, what I'm going to cover is solving radical expressions. So what happens when you have the cube root of x minus 9 equals -1? How can I solve that? I'm going to give you like 3-minute preview of how we actually would solve it. And the reason I'm going to give the preview now is because we can verify with Desmos. So I want to just show you what that looks like. And we'll do a lot more of these on Monday, but okay. So we have the cube root of x minus 9 equals 1. So just because you have a cube root in there, fourth root, square root, whatever it is, doesn't mean you cannot solve the equation. We still can solve the equation. We still use the same rules that we used before. We just have to use a little bit more information. So just like any equation, we want to get x by itself first, right? So in order to do that in this equation, I'm going to add 9 to both sides of my equation very largely. And I get the cube root of x equals 8. Okay, you might know what this is already, but it's okay. So there's a couple ways now that we can solve this. So one way, well, they're both kind of the same way. Actually, never mind. I was thinking it was something else. I was thinking x equals 2, but that's actually not right. So there's a couple ways that we can solve this. So one is that we know that if we have the cube root of x, okay, equals 8, and we kind of want to undo a cube root or a square root, we could actually cube this side of the equation, and we would also cube this side of the equation. So the cube root of a cube just leaves us with x, and 8 cubed is 64 times 8, which is 512. Okay. Another way that you could think about this is when we were here at this equation, we could rewrite this as x to the 1/3 power equals 8. And it's a 3 there. And then it's the same process, however. We would, to get rid of 1/3, you would multiply by 3. And you would end up with x equals 512. So the reason I wanted to show you that really quickly is that what does this look like if I graph it? Because that's always kind of in your back pocket when you're solving equations. You can always pull up your graphing tool and just graph and see where it intersects to see if you're in, obviously this problem you can't just graph, or these problems you can't graph everything, but it's always in your back pocket to check if something is correct by graphing. So what I mean by that is if I go back to Desmos and I say that my left-hand side of the equation is the cube root of x minus 9. That's my left-hand side. Oh, it's way down here. Okay. And the right-hand side of my equation is y equals -1. And you have to put this into Desmos so that it knows that you want to graph it. And you also, that's how you would put it into a TI calculator. Okay, so then I go here, go here, go here. And I can see that I need to figure out where these two intersect to find out what is true. And I know that I'm going to have to zoom out a lot to figure that out because I already solved it, right? So we know, if I zoom back in here, somewhere along here, it showed me the point here. At 512, -1, the two intersect. So just always remember that's kind of the tool in your back pocket to figure out where they intersect. And you can see here they're not intersecting. They intersect here and they go back apart. Okay, so that's all I had for today. We'll go over 6 on Monday, and then we'll be done with 5 and 6. So be ready for homework due, and not this Monday, but the following Monday, and then a test coming out on Monday as well. Thanks for coming today, Connor. Thanks for anybody listening online. Have a good day.